Ooh, this is a good game.
So, what is mathematics? At its core, study of patterns and relationships. And yes, maybe Sanaya could make it more fun at times, but I tell you what, man, studying some of those patterns and relationships is real fun and real beautiful if we let it be.
Mr. Kenny,
Oh, Mr. Kenny! Okay. So, here's the thing. We got to discover these patterns and relationships, and we're about to focus on them some more to understand how things operate. And there's the last couple lessons that we have. So, as a quick recap to get us prepped for what we're doing today, what is an inverse function? Say that one more time. So close, you're mixing two things. It's a reflection across y equals x, which causes inputs and outputs to transpose. Right? It's a reflection across y equals x, causing my inputs and outputs to transpose. And then we talked about this number yesterday. What is the number E? It is a letter, but weirdly enough, we established it as a number yesterday. It's something like 2.7. 2.718 is the normal approximation that we use. Yeah, it's 2.71828. We usually go to that 3 decimals. So, for example, or to compare this to, when we talk about the number pi, what do we usually approximate pi to? 3.14. But it goes well beyond that. 14, 159, 26, yada, yada, yada. Okay? So, because it's an irrational number. Same thing with E. It's an irrational number. It goes way past 2.718, but that is the number E. Remember, that was that limiting factor when we had A equals this compounding interest, R divided by K raised to the KT. When K approached what? Infinity, right? When K approached infinity, when my rate was 100% and my initial investment was 1, that expression approached 2.718. And that's why it's the natural base, the natural number. So when we start compounding infinitely, meaning that we never stop, it's called continuous compounding, we get that number E. Does anyone remember why it's called the number E? So it is the natural base, but where did that E come from? That would make sense. It was Leonard Euler, right? So remember the mathematician who discovered it, I think this is how you spell his name, Leonard. I know the last name is Euler. Leonard Euler was the mathematician who really discovered it. You talking about the last name? I do know that last name is correct, Euler. But he's like German or some European with an interesting spelling, especially because he was old school. I think 17th or 18th century. But that's his name. Recap there. So we're jumping back quickly. Actually, I think we're done with lesson 2. Y'all are focused on lesson 3, the inverse of the exponential function. I have to start in lesson 2 with the other classes. So we talked about the natural base. Notice here, this is on page 114. If you ever need to go back to the number E, it's got a lot. So 18th century. It's got a lot of information, some more decimals, information like that. He was Swiss, that's what it was. We are on lesson 3, which is what started on page 125. And what are we studying in 125? As a preview. Logarithms. That's what we're looking for. It's a new pattern, right? That's something I need us to pay attention to. The fun new pattern that we get to explore, Sanaya. So, we're looking at logarithms. What a logarithm in and of itself is, the function, common logarithm, natural logarithm. Pay attention to your key terms and your learning goals out of each of these lessons. So, I don't think we did too much here yesterday. I think the only thing we established was that this notation stands for what again? That is the inverse function of f of x, which is 2 to the x. So this curve right here is the inverse of what type of function? Exponential, right? So we're looking at the inverse of an exponential. We see that clearly because this is a reflection across y equals x. We can see it clearly in the table because what's happening to my inputs and my outputs? They've been transposed, okay? So here's what we're going to do. I'll give you all a vote. Do you want to fill out the domain through the, which we're going to skip intervals of increase and decrease. Do you want to fill out this table at your desk or at the vertical surfaces? Raise your hand if you want desk. Raise your hand if you want vertical surfaces. Let's do this then. Grace, you wanted vertical surface, right? So Grace, Marshall, and Miracle and Hayden, y'all work on this vertical surface over here. Eliza, if you want to work at a desk with this group, you can. And who wanted vertical surfaces over there?
Me.
Let's just do this. I'll let your whole group work at that vertical surface. All right, let's fill out this table. Please do notice this is domain and all this information through what is I'm looking for? Oh, for f of x, the exponential function, and this is the inverse. If you need some help or reminders on domain, range, and all these different features, we did something like this on M3-110. It's not necessarily going to be exactly the same, but you can refer back to that to look at some examples of domain, range, and all that fun stuff. Alright, so let's get to work on filling out that table, figuring out what those features are.
Hey, what's up? It's like that.
So guys, let's make sure that we are focused, helping each other grow and learn. Answering these questions. Check in with each other, discuss. Practice on these exact skills, but let's break this down and let's look at it. So, in behavior seems to be a trouble for some of us. We got to know how to do in behavior though. So, let's discuss. First off, what is the domain of f of x? Domain of f of x. Okay, so negative infinity to infinity is Lily Kate's answer. Does anybody want to push back on, ask a question about that domain? Or add on to? Nobody? Because I see brackets over there on domain. I see infinity to infinity over here on domain. Oh, that's the inverse. Just kidding. So on the function, you got negative infinity to infinity. But we have brackets over here. Should we have brackets or should we have parentheses? Why do we have parentheses? On the domain, y'all have negative infinity to infinity with brackets for f of x. Should it be parentheses?
Yes. Oh, an f of x?
Uh-huh.
Wait, which one?
Domain.
The left side or the right side? Oh.
Notice the entire domain for f of x, y'all have brackets on. Well, remember, this is that's the inverse function of f of x. Domain, y'all have brackets.
Oh yeah, because they told me to put brackets.
But we should have parentheses. Remember, you only use brackets if you have that actual number or value, and we can't get to infinity. Okay? Hey, it's okay, Miracle. We're learning from it. Guys, so I'll point this out. I did decide, just looking at this, this is why I want vertical surfaces. We'll go back to it. I cannot see your thinking if all you do is write it in the book. Right on it. We're going to go back to vertical surfaces for the next part because it helps me see where we are misunderstanding things. But do notice, f of x, does it ever stop going to the left?
No.
No. Does f of x ever quit going to the right? No. So the lowest x is negative infinity, the highest x is positive infinity. And that's what you want to think about. What is the lowest, what is the highest? Minimum and maximum. Range for f of x though. I saw a lot of 1 to infinities. Does anybody want to push back on 1 to infinity? Or does anyone want to add on to 1 to infinity? Desiree, are you saying 0? What was this for?
He was asking me a question.
Oh. We can ask it. Let's have whole class conversation at this point. Does anybody want to push back on that range? Or add on to, or ask a question about? So you're thinking 0? And this group over here, y'all also said 0 to infinity for the range. Why is that? How do you know it's approaching 0? Let me ask this question actually. For those of us who did say 1, why were we thinking 1? I need to address this because I will go ahead and confirm. It should be a 0 here, but we need to know why it's not 1. So why were we thinking it was 1? Say it louder.
It was plotted on the graph.
I can't hear you.
Because it was plotted on the graph.
It was plotted on the graph. So you're talking about this y-intercept right here? But I want you to notice, are there y values below that point? Well, there is one right here, right? And there's one right here, and right here. Notice, what is this curve approaching? What key line? Well, it's approaching the, what do we call this line? X-axis. And what is the y value on the x-axis? 0. Notice though, we do use a parenthesis here because does it ever actually get to that 0? No. Yes, ma'am?
So if it's approaching 0, we just put it 0.
You put a 0 and then you put a parenthesis. So that parenthesis there means that it's going towards it, but it doesn't actually get there. We use a bracket when we actually have that value. We use that parenthesis when we don't get it, when it's approaching it. And let's redo, I should have done this before. Instead of y-intercept, let's just do intercepts. That's not how you spell intercepts. So f of x, what intercept does it have? Y-intercept of 0, 1. What about x-intercepts? Why not? Right, it never gets to the x-axis, so there are no x-intercepts. I'm going to come back to asymptote. This one causes a lot of people difficulty. Now, I will say this. If I were you, if I was going to do an asymptote, I would do my end behavior first. How many ends do you have for this graph? 2, right? There's at least 2 ends. So, the left-hand side and the right-hand side. I'm writing it over here so I have extra room. But on the left-hand side, z, as we go to the left, what is x going towards? Z. So z, I want you to think about it. X, right here. That's going left and right. But if I think as I go to the left, is it ever going to stop going to the left? No. What do we use to represent something that doesn't stop? Infinity, but it's going to the left, so which infinity is it? It's on the negative side of numbers, so we would say it's negative infinity. So as x goes to negative infinity, what's y going towards, Trayana? No. As x goes to the left, as we go towards negative infinity, what is the y going towards? Positive what? Infinity? Okay. Anybody want to add on to, ask a question about, or push back on that being my end behavior on the left-hand side?
I believe it's 0.
You believe it's 0? Why is that? Notice y approaching infinity says that the graph is going. Well, notice, hold on, if I say y approaches infinity, that means the graph is going up. On the left-hand side, is this graph going up? No. What's it getting close to? But what's that line called to help us see it better? The x-axis. And what's that y value on the x-axis? 0. So remember, Trayana, when we were talking about this range over here, how it's getting close to the 0? That's that 0 for the end behavior. Okay? Marshall, right-hand side. What is x approaching? as I go to the right, what is x approaching? Why are you thinking that? Okay, it's on the right side of the y-axis. So why is it positive infinity and not like 5 or 6 or something like that? Okay. Okay. Can anybody add some more detail onto why it might be that positive infinity?
You got an arrow, so that means I'm keep going.
So remember, right hand in behavior, I want to look at that right hand side arrow. That means it's going up and to the right. Is it ever going to quit going to the right? So, x goes towards infinity. What I do want to remind you, and I mentioned this yesterday, hey guys, notice the end behaviors match the domain. On the far left side, x approaches negative infinity. On the far right side, x approaches positive infinity. So Jamarcus, what's y approaching? Infinity? Why are you thinking that? But that was the x approaches infinity because it's going to the right. Not sure then? Can anybody add on to then? Because it's what? So remember, if I'm talking about y, I'm talking about up and down, right? As it goes to the right, it's also going up. So when I look at this, that's my end behavior. Final questions before we continue talking about some of these other features. So, asymptote. What do we mean by an asymptote?
Where is approaching?
So, it's a
Where it doesn't.
line that the function approaches at an infinity. Does anyone see in this end behavior a line that the function might be approaching at an infinity? Y equals 0. Notice, at this infinity, the y approaches 0. So what's my asymptote? Y equals 0. That's why I recommend doing that end behavior before the asymptote. You can see it clearly here. Like, you don't have to do that. We can see that it approaches the x-axis, but that end behavior helps a whole lot. And I think I saw Jacoby actually writing this in his book. When he was writing his asymptote here, he didn't just say y equals 0, he said x-axis. Is that right, Jacoby? Did I see that correctly? Right? It's approaching the x-axis. That's the line y equals 0. Now, does anybody know a cheat code to help me get all those features for the inverse function of f of x?
Yeah, why you go to the right?
Wait, so the domain and range switch? So then just looking here, not looking at the graph, just looking here, this domain should be 0, comma, infinity, and range should be. So let's check that in the graph. Domain. Does the inverse function of f of x ever go to the left of that x value of 0? No, it approaches the x-axis. And then it continues going to the right for forever. So what's the maximum x value? Infinity. Range. Once again, let's see. Lily Kate, what does range refer to? Just in general, what do we mean by range? You're thinking about range from a statistical perspective, not just how far it goes. Range specifically refers to what, Jayla? Remember, y values, right? Yeah, and I will say interval notation, minimum to maximum, but when I ask range, you need to immediately think about y values up and down, right? So I've got an arrow here. What's the lowest y value? Negative infinity. What's the maximum y value? Positive infinity. It's going to the right, but it's also going up. Intercepts. What's my y-intercept? It's not 1. Right? Over there, I think we were talking about an infinity for the y-intercept, right? It doesn't actually get there, though. Instead, this y-intercept becomes an x-intercept. What x-intercept? 1, 0. Why does that make sense? Inputs and outputs transposed, right? 0, 1 became 1, 0. The y-intercept became an x-intercept. That's exactly right. So now I want you to think about this. We're going to look at in behavior in a second, but does anyone know what the asymptote for the inverse of f of x should be based on what f of x is? Say again. The asymptote is 1, y equals 1. Okay? Anybody want to push back on or add on to that? Okay. Naisha, you want to tell me why you think it's 1?
Because we're supposed to get the asymptote from the x-axis.
Say it one more time.
We get the asymptote from the x-axis.
So we do get the asymptote from the x-axis. So if I look at this x-axis, wait,
That's the one.
that's the y-axis. So you're saying I get the asymptote from here. So you're using this one right there?
Yeah.
I thought that's an x-intercept. So an x-intercept is the same as an asymptote?
No.
Remind me of this, guys. What did one? There's two things to remember here. One,
Wait. Oh.
okay. What is an asymptote? So a line that the function approaches at and infinity. And two, what happens to my inputs and outputs? They transpose. So why do you still think it's a y equals?
Oh, well, that is, it's x equals
X equals what?
1. 0.
What is the line that this function approaches? It approaches the y-axis. The line that function approaches the y-axis, your asymptote does not have to be horizontal. The asymptote can be vertical. And it is in this case, because my inputs and outputs what? Transpose. What are your questions about that asymptote? Okay, we will see it more clearly here as well. For the inverse function of f of x, on the left-hand side, what's the in behavior? What's happening to x on the left-hand side? What's x approaching? 0? Why do you think that? X approaches negative infinity or 0? X approaches, notice, does it ever go past the y-axis? No, so the x approaches, which makes sense because what's the lowest x value in the domain? 0. So on the left-hand side, x is approaching 0, and what's y approaching? Remember, it's going down towards, hey guys, what was my in behavior? What happened to it? Transpose, it switched. That pattern of inputs and outputs transposing will never abandon us. So what about the right-hand side? What's x going towards on the right-hand side? X is going to the right, to infinity. But look again. On the right-hand side, it goes to the right and... So what's y going towards? Notice, Trayana, the inputs and outputs switch. But these are the same, so it stays the same. But you can see it on the right-hand side. As it goes to the right, this function is also going up. What are your questions about those features? Notice once again, with an inverse, what's happening? Because it hasn't changed for a week and a half. The inputs and outputs transpose because of that reflection across y equals x. And so hopefully you have a hint so far. What is the name of that function that we're looking at there, this inverse? It's a logarithmic function. Logarithm is the noun, logarithmic is the adjective. And so we're going to look at this on the next page. But do note, that shape, that curve, is known as a logarithmic function. That's the inverse of your exponential. And so here's what we mean by a logarithm. A logarithm seems to be a really scary word to a whole bunch of high school students when they first learn it. Don't let it be. And I think I mentioned this yesterday. What is, say, I'm going to make this up. What is the cube root of 8? Anybody know that off the top of their heads? Cube root of 8. It's what? 2? Why is the cube root of 8 2? So 2 cubed is 8. So a cube root is just the inverse of that exponent, right? That power, I should say. So when I look at log, shouldn't have used that number because that's what they have exactly. Actually, that can work well. Log base 2 of 8 equals 3. If I am asking you for a log base 2 of 8, all I'm asking you is, hey, 2 to what power is equal to 8? So, with roots, what I was asking is, hey, what was cubed to get 8? We're finding the base with roots. With a logarithm, I'm looking for like what? What's the variable in an exponential? It's the exponent. So guys, with a logarithm, all I am looking for is the exponent. That's the difference. A root, roots look for the base. Logarithms look for the what? Exponent. That's it. So when you ever have someone who says, hey, this logarithm is really tricky. Nope, just, hey, what's the exponent? May not be an exponent we know off the top of our heads, but all that is being asked is what's the exponent? So what exponent goes on 2 to give me 8? What is it? 3. So log base 2 of 8 is 3. Now, I'm going to show you some notational things. They have it in the book. But the traditional way to write a logarithm is you can say log base of an argument equals an exponent. Or log base b of a is equal to n. That's what we traditionally do. Notice they give it with examples of numbers over on the left-hand side over there. Log base 2 of 8 equals 3. That's how you read that. Log base 2 of 8 equals 3. And so before we get to these worked examples here, I would pay attention to those in a second. Let's do a couple of our own. Log base 4 of 16. What is it? 2?
Why is it 2?
It's a great question. Ethan, why are you thinking that? So I wanted 4 to some power that equals 16. What is the exponent? Does 4 squared equal 16? Yeah. So, again, when I evaluate a logarithm, what am I looking for? An exponent. Notice the base of the logarithm is the same as the base of the exponential. That's a key thing to note, is that the base of log is the base of exponential. That's all we're looking at. would log base 2 of 32 be? Okay, so what you're telling me is that 2 raised to what exponent? 16 is equal to 32? Let's check that in the calculator. I think what you might have been thinking is 2 times 16.
Yeah.
Mm-hmm. But how many times would you need to multiply 2 to get 32? As you can play around with this in the calculator. 5 times? So log base 2 of 32 equals 5, because 2 to the 5th is equal to 32. That's all a logarithm is. It's an exponent. You can get super lost with logarithms because it is this new notation. But if you can go back to the foundation that a logarithm is an exponent, it's super easy to tackle. Now I'm about to show you one thing to help this sink in, but it is going to seem wild on the surface. Log base 16 of 4. Yeah, I know, right? So a square root, but we need an exponent, right? You are 100% correct that the square root of 16 does equal 4, but I need that to be written as an exponent. And guess what? You can write radicals as exponents. So why don't you find out how to do a logarithm in the calculator? If you pick up the calculator, does anyone see that idea of a log anywhere?
Yeah.
Say that one more time. Control and then 10 raised to the x is what you want. Notice 10 to the x is an exponential, and what's the inverse of an exponential? What's the inverse of an exponential called? Logarithm, right? So we hit control, then we do 10 to the x, and you should see a log, a little square here, and a square here. And so what's going to go in this base? 16. The argument is 4, and we get, or 1/2. There's a reason why I want you to see it as 1/2 for a second. So 16 to the 1/2 is 4. But I want you to remember that all of you originally, or several of us, talked about the square root of 16, right? So square root of 16 must be the same thing as 16 to the 1/2. So hold on to that. We're going to come back to this in a second. Are you checking that?
How is the same thing?
I know. It's a way that we have defined rational exponents. I'm going to show you a couple more, see if we can find the pattern. So, log base 81 of 27. I know it seems wild, right? But type it into the calculator. It's 0.75. Okay? And so that would be the same thing as 3/4. So, 81, what's the exponent on the 81? So remember, this is not the exponent. What is the exponent? 3/4. Remember, what the logarithm equals is the exponent. So 81 to the 3/4 must be what? Equals 27. Do this for me though. Do the 4th root of 81 cubed in the calculator. Let's check that really quickly. The 4th root of 81 cubed, you can find any radical above the little caret symbol. So if you hit control and that little caret symbol, it'll allow you to do any radical. You need that 4 inside of that radical symbol. Or at the... Oh, did I never collect the surveys?
No.
My bad.
Mine
Why does he have carrots?
If It should have deleted unless you said don't save. Did you say don't save? Oh, okay. So I can still collect it. There you go. Okay. So if you hit Control and then the that caret symbol, then you should see a little. So hit Control, the caret symbol. Okay, you see where it says x squared? That little arrow is called a caret. If you've never heard that before, that little arrow is called a caret. Not like the thing that a rabbit eats, but in the first box, you want to hit 4, go inside of the radical, and type in 81 to the 3/4. Control, and then. Yeah. So 4 is on the root there. So, what is the 4th root of 81 cubed? 27. So, 81 to the 3/4 is equal to the 4th root of 81 cubed.
Wait, did you get a decimal?
0.75 here? Come on, here.
I got 2 points.
Did you make sure that that 4 was inside of that hook right there? Oh, no. Remember, 4th root of 81 cubed. One, that needs to be an exponent. Cubed. Okay? So, 81 to the 3/4 is equal to the 4th root of 81 cubed. The square root of 16 is equal to 16 to the 1/2. Let's do one last one. Log base 32 of 4. Log base 32 of 4. We got one more here. 0.4. And 0.4 is the same thing as 2/5. So, I should write this the other direction. So 16 to the 1/2 equals. So when I'm writing this as an exponent, what is the base for the exponent based on that logarithm? The base is 30, what? 32, right? 32. What's the exponent? 2/5. And 32 to the 2/5 is going to equal 4. Let's make a prediction. Does anybody know or have a prediction about what the radical version of this would be? So you think it's a 5 right here on the outside in that little crook? And then what?
The 2 on top of that.
So the 32 squared?
Yeah,
So what is the pattern?
like this.
Not quite.
They sweet.
Look,
Like all of them.
Fraction breaks apart.
that fraction breaks apart. So let's look at the pieces of the fraction. Where does the numerator always go? So the numerator becomes the exponent of the radicand. What does the denominator become? Yeah, it'd be nice if there was a word for that thing, isn't it? Wouldn't it? It's called the index.
So it stays the same?
What do you mean? What stays the same? Don't use the word it. What do you mean, what stays the same?
Like, but when you do the exponent and the number outside together?
So like this exponential or this exponent and this radical are the same?
Yeah.
Mm-hmm. So these are equivalent, different forms, but they mean the same thing. Whatever this denominator is, that's the index of the root. So that's the type of root. Whatever the numerator is, that's the actual exponent. That's literally what it is.
Can you write it in?
So, denominator of exponent is the index or type of root. And numerator is the exponent. And the numerator is the exponent. Okay? So you can read this.
As the 26 under the radical.
So 27 be underneath the radical.
The 3 is the, the exponent. No, the index is 2. Wait.
The denominator is the index or type of root.
Oh, yeah, okay. It's 2, 6.
So the way that you can read this is 27 to the 2/3, or what I would actually say is the cube root of 27 squared.
Alright.
And I will point this out, you can do them in any order. Does anyone know what the cube root of 27 is? So what was multiplied 3 times to get 27?
3.
3. 3 cubed is 27. So this would be the same thing as 3 squared.
I think the same thing.
3 times 3 is 9, 9 times 3 is 26.
Okay, but 9 times 3 is 3 times 3 times 3.
That's
So-
no, it's not.
The cube root of 27 is 3, and then 3 squared is 9. So 27 to the 2/3 is 9. That's how we would read that, how we make sense out of it. So the cube root of 27 squared. And so I would do the cube root, or I always do my roots first. But
You do have to get the cube root of 27, but the index and the,
so remember, the index is the type of root. So when we say the cube root of 27, the index, what's the root is 3.
Okay.
Does that make sense? Yes, ma'am. It came right here. So what I did is I did the cube root first, and then I squared it. Because here's the thing, anybody know 27 squared off the top of their head?
Yeah.
Yeah? I don't, okay? But I know the cube root of 27, so I do the cube root first to make the number smaller before I square it to make it bigger. So I do the root first. Now, at the same time, could I just use a calculator?
Yes.
Yes, 100%. Okay, so that gives us some background. That is an Algebra 1 skill that we are supposed to review, and I didn't have a chance to review before, so I wanted to include that here.
That's algebra 1?
Yep.
We ain't learned that.
We never learned this.
Okay.
How?
You can say you didn't learn it, and how is it an Algebra 1 skill? If you go look at the Algebra 1 course of study for the state of Alabama, it is an Algebra 1 skill.
Who didn't do that?
Hey.
Oh, I forgot
Hey,
to feel.
we're not trash talking to the teachers.
We just saying, like.
I know. I know that we didn't learn it. I'm just telling you that that is an Algebra 1 skill. Okay. But I will also point out, it's not terrible. If you understand that the denominator is the type of root and the numerator is the exponent, you're golden. Now, final couple of details that I'm going to look at right here. When we have some examples in the book, notice log base 10 of 1,000 is equal to 3. Why is that? You always want to think through logarithms in their exponential form. Why is log base 10 of 1,000 3?
Because 10 squared,
10
cubed,
cubed is
1,000.
1,000. Remember, the base is the base of the exponential. What the logarithm equals is my exponent, and 10 to the 3rd is 1,000. Log base 4 of 16 is 2. Why is log base 4 of 16 2? 4 squared is 16. And this is important for functional notation to think through what we're about to study. If y equals b to the x, what is the inverse equation?
B equals Y.
So log base b of y. So what was my output has become my input. And that's going to equal x. Notice how the bases stayed the same. What was my output has now become my input, and what was the input has become the output. This is the inverse of that exponential function. We studied this exponential function forever ago and we reviewed it recently, but notice this is the exponential, so base exponential. This is the basic logarithmic function.
This will be on 10.
Some with it, not 1,000 things.
You got it.
We do not have a napkin. We don't have time, unfortunately.
You don't have like worksheets, right?
Yep, we got the textbook.
Gotta do it. I'm not ready to
Listen, can we need something better than this work,
We are going to apply this with problems in the textbook.
We're not gonna get no worksheet.
We got work.
So, looking here at the next page, and by the way, there are practice problems right there that you can work through again. But looking here, I need y'all to pay attention to this. Remember, this exponential and this logarithm are inverses. But whatever x is here, that's the same as this x here. Whatever is true about this base for the exponential is true for the base of this logarithm. So when we talk about x, when we talk about this exponential function, what was the domain for the exponential function? What was the domain for the exponential function? You can literally look back to the getting started a second ago. The domain was negative infinity to infinity. So is there anything that x cannot be?
No.
No. So there are no restrictions. Right? Domain of y equals b to the x was negative infinity to infinity. There's no restrictions. That x can be any real number, I will say. So I guess there could be the restriction, has to be a real number. But any real number. So the domain is of this is anything. And so remember, that also meant the range of the inverse is what? The same thing. So that's the reasoning why there are no restrictions. So notice we're figuring out what the output can be for that logarithm based on the input for the exponential. Looking at the base b, were there any restrictions on the base for the exponential?
No. Yes. 100% yes. He's shaking his head, yes, so it yes.
Say again.
Big brother.
Say it one more time.
He's not.
Not restricted by x, but when we did this before, right? We talked about exponential growth, we talked about exponential decays, and we looked at that graphing thing on the calculator and we changed what the value for b was. And at some points, we got this really funky thing that looked like this. And was that an exponential function?
No.
So what base values did not create an exponential?
Oh yeah, lower than 0.
So if the base is lower than or even equal to 0, there was one other number that the base could not equal, and it gave us this. So the base cannot equal 1. So the base cannot equal 1, the base cannot be less than or equal to 0. Hey, so guess what? For a logarithm, what can b not be? The same exact things. The exponential and the logarithm are telling the same story. So this did not work for an exponential. It will not work for a logarithm. So these bases don't create exponential functions.
Okay.
Oh, that's a semicolon.
Yeah, that.
Yes. Yep, that's a semicolon.
That's a who?
Semicolon? Right here.
One dot comma down.
So notice how I put a slash through it to indicate that's what b cannot be. B cannot be less than or equal to 0. B cannot be 1. Those bases don't create exponential functions, so we cannot use them for logarithms. Anybody know what y can or cannot be?
C.
Okay?
3.
Okay, so remember, y equals b to the x. That's the what for an exponential? Okay, so what is the collection of all those y values then called?
Range.
So that's the range for the exponential. Y would also be the what for the logarithm.
Wow.
It'd be all the inputs. So what were the restrictions on the outputs for the exponential? Because they were the same for the inputs of the logarithms.
Ain't no restriction.
Y is the input for the logarithm, because remember that was the output for the exponential.
Ain't no restriction.
They could be sweet tooth.
Well, they would be the same, but listen, I'm asking what are the restrictions? Go back and look at the getting started. What were the restrictions on the range for y, which were the same as the restrictions for the domain of the logarithm? Okay, what is the range for the exponential? 0 to infinity. What was the domain for the logarithm? 0 to infinity. So what can that y not be? Y cannot be less than or equal to 0. Remember, the collection of all my outputs is called the range. And the range here, Sanaya, because you were saying that something about it not making sense, the range here is my domain for the logarithm. You looking at it? The range here is the domain for the logarithm because they are inverses. The inputs and outputs transpose. That's why. So y cannot be less than or equal to 0. That is the range of exponentials and domain of logarithms. Okay. And I really have to say, I'm sorry for the last 2-3 weeks, but I've done way more direct instruction than I like to, but gotta get through this before the end of the semester. Okay? In the book, they do this thing called a triangle of power. I think it's goofy, but you can use it if it helps you. What they always do is they do the base of the logarithm here, raised to the exponent equals the argument, and so you can rearrange it, different things like that, to figure out what the values are. I think it makes more sense to just create an exponential out of that logarithm, but you can use that. We literally just did that. Okay. I don't know why I have that in there twice. Okay, what I will do is, we don't have a ton of time. I'm going to give you about 3 or 4 minutes to just rewrite A, B, and C in exponential form. You don't have to do the triangles of power. Rewrite A, B, and C in exponential form to figure out what x is in each of these cases. So rewrite each of these in exponential form to figure out what x is. Yes, ma'am. If your teacher allows you to. So come on guys, let's rewrite these as exponentials. Figure out what our variable is. Let's actively talk. See if people agree on how to set up the exponential first. So that's the logarithm. I would rewrite it as an exponent, like here. So they have this logarithm, and it's written as this exponential. So think about it. When I look, So yes, how we did all that. So when I look at this logarithm, what's the base for the exponential? 10, okay, so 10, what's the exponent?
I got B.
1,000. The exponent would be x, right? The logarithm equals the exponent, so 10 raised to the x would equal what? Let's figure out what x is.
For real, bro?
You see me sleeping. It's the room, bro. Can you explain it?
So remember, when we talk about that logarithm, it's a base, an argument, and what is a logarithm equal? And
I put it.
A, B, and C. What's your base? How is
so
it?
what's the base for the exponent? 10, so 10, write down 10. And then what's the exponent going to be? Well, just like write the exponent there, so 10 to the x. We're going to figure out what x is in a second. But what is 10 to the x equal?
Oh.
Curse
So it
it.
equals the argument of 10. So
This
just
is
rewrite your exponential.
so this is
You can try that, but rewrite each of those as an exponential and then we'll discuss. Yes, sir.
Okay.
Yes, sir.
Still.
What's up?
Okay. Oh, wait.
Okay, rewrite it as an exponential.
Oh,
okay. So right now, write it as 10 to the x, and then tell me what x equals. So like you figured out x was 3, but write it as the exponential form, and then tell me what x is. That'd be part of your evidence of understanding, telling me why you know it to be that. Okay? Well, what's the base for b? What's the exponent? The exponent's 5. Remember, the logarithm equals the exponent, doesn't it? So 5 to the 5th is equal to
is this somewhere right?
right? What was the input for the logarithm becomes the output for the exponential. And then what is 5 to the 5th? You gotta calculate it.
Draw triangles of
You said
how-
these words about that. You don't listen.
Okay. What?
Wait, look at this right quick first.
Okay. You guys, 20 more seconds. What's up?
So, you ain't have to do that, right?
You didn't have to do the triangle power, but it helps, right? So if you like that, 10 to the x equals 1,000. So write it as an exponential now. 5 to the 5th equals x. X to the 1st equals 9. So write it as an exponential to figure out what x is. All right. So let me see, Lily Kate. What is the exponential for a? So 1,000 equals 10, like that? Okay, hey guys, no side conversations. We're having a whole class conversation at this point. So raised to the power of x, and so x ends up equaling 3. 10 times 10 times 10, so 3 10s multiplied gives me 1,000. Part B here. Sanaya, what's the exponential for part B? So, say again. 5.
Oh, x equals 5 to the,
So 5 to the 5th is equal to x. And so what did x come out to equal?
3,125.
3,125.
I did it backwards.
I mean, you can do x equals 5 to the 5th. Do you have this same idea though?
Yeah.
The order doesn't matter. Like you can do this.
I did 3,125 equals 5 to the 5.
I mean, that's true. That's what x is, right? I was asking for an exponentially version of this first.
Bless you.
So 5 to the 5th equals x. Then tell me what x equals. Yes, ma'am.
It's okay, we're not there.
So remember, the base of the logarithm is the base of the exponential. Okay? The logarithm itself is equal to an exponent. So what the logarithm equals is my exponent here. And whatever the input of the logarithm was, that's the output for the exponential. Okay? So when I look at log base x of 9 equals 1, what's the base of the exponential, Eliza? Well, what's the base of the logarithm? The base is Remember, it's log base argument equals exponent. So the base is, by the way, I need y'all to pay attention to this. Some of y'all, I've already started to see it, and many more throughout the rest of your life, will write this base in line. But do notice the base is a subscript, meaning it's written below. The argument is written in line with the logarithm. The argument is not an exponent. It's log subscript base of the argument equals an exponent. So the base is x. What's the exponent? 1. That's what the logarithm equals. And it equals 9. So what does x equal? 9. Okay? So a logarithm is equal to an exponent. That is it. Pay attention to your notation though. That subscript needs to be a subscript. Alright. So notice how they talk about these features here of what the base of that logarithm needs to be, what the inputs need to be. If I was given this function right here, this exponential, notice they've defined it as h of x equals b to the x. And so they've literally just done, hey, if x is 2, I get b squared. If x is 1, I get b to the first. If x is 0, I get 1, because anything to the 0 is 1. How would I figure out what the inverse of that function would look like, what the logarithm would look like? No? Go, keep going with that. Guys, I'm trying to figure out the inverse of h of x. How would I sketch that on this graph? So the line y equals x? Why do I need that?
Just to make sure you're doing it right.
There we go. We've got to remember, what is an inverse? It's a reflection across the line y equals x. And so I'm going to use that line to help me here. Now, a couple of key points. What's 0, 1 going to become? 1, 0. And by the way, does this sketch need to be perfect? Heck no. But, you see right here where the curve is approaching the x-axis? What does the logarithm need to approach? The y-axis. And so it's got to look something like this. All right, we're going to add more detail to it in a second. But what's this point negative 2 comma 1 divided by b squared going to become? We have this point right here, negative 2 comma 1 divided by b squared.
1b squared.
1 divided by b squared,
And then negative 2.
comma negative 2. Right? Notice I'm going across here. So how did you get that?
You switch them.
So you transpose your inputs and outputs. I know it sounds wild, but that's all it is, guys. My inputs and outputs are what? Transposing, because it's an inverse function. I don't quite have room to do this other one right here, but boom. Say again. Your what?
You move too fast.
I'm going to slow down in a second. Okay. Okay. Desiree, you got a question?
What does that stand?
I can't hear you. Say it loud.
What does that stand at the bottom?
Right here.
Yeah.
It says 1 divided by b squared, comma, negative 2. Because what's happening to the inputs and outputs? They are transposing. So this point reflected across y equals x, and the input and output transposed. That's it. It's an inverse function. Okay? What are the coordinates of this point? B, comma 1. Notice how I just kind of reflected perpendicular to that line and went the same distance to the other side. Right here. About the same distance to the other side. What's that coordinate going to be? B squared, comma 2. So that's what it's going to roughly look like. Okay? I want y'all to notice something. Why is there a 2 right here for the output? And it's not just because the inputs and outputs transposed. What is a logarithm? It is, when we evaluate a logarithm, we're getting an exponent. What's the exponent here? 2. What's the exponent on this b? On this, just b to the first, it'd be a 1. If I have an exponent of 0, what's the argument, or what's the output? If I have an
It's a joke.
exponent of 0, the output is 1. So when I have an input of 1 for a logarithm, the output is 0. You've got to remember that at the end of the day, for logarithms and exponentials, the inputs and outputs switch. Right?
What about the fraction part?
Yeah, so we actually talked about this the other day, but 1 divided by b squared, a negative exponent is what indicates that division. So what's the exponent? Negative 2, right? 1 divided by b, that's the same thing as b to the negative 1. And so what's the exponent? Negative 1. Does that answer your question? And so that's why they went, and I don't love that they did that, I wish they had left it this way to be able to see that more clearly. But yeah, the fact that we get that fraction comes from that negative exponent. Negative exponents indicate repeated division. Okay, what are your questions about the sketch of this inverse, one as the inverse of a logarithm, but in general as an inverse? Before we continue. Okay, so we all have our notes on that. And we're going to put this here, write the equation for the inverse of h of x equals b to the x. And so we're going to want to put that on this graph right here for number 2. What would the equation of that be? How would we figure that out?
The log.
Why? Yes, we will use the log.
Because I don't know how to say it.
Look, if we remember y equals x squared, how do we find the inverse of y equals x squared? We took the square root so that my input became the output. So the square root of y equals x. This, remember, is when we transposed to find out that the square root of x equals y so that I could use the inverse function notation. So what do I need to do to get started here? If h of x is equal to b to the x, what can I substitute in for h of x? What's going to take the place of h of x? Y. Y equals b.
Y equals b to the x.
So what's the inverse of that exponential?
Bx could be, but it could be log x, thingy thing.
Log base.
Log base b. See how the base is the same? But what was my output is going to become my input equals x.
Yeah, that's all I'm trying to say. I just couldn't say it. I don't know how to say it.
So transpose my inputs and outputs at this point. But what's going to be the notation that I want to use if this is an inverse function, which this is an inverse function? What's the notation that I use to indicate that this is the inverse of h of x? H with that superscript of -1 of x equals log base b of x. So that is the equation for that logarithmic function.
Are you 30?
Okay? We have 2 last details, and then tomorrow we will spend the entire day practicing working with logarithms. We will have some type of understanding check tomorrow, but last couple details. Well, there's no way to test on Thursday. We're going to have to test on Friday, so we can have the understanding check tomorrow or Thursday. We'll just talk about it tomorrow. But I need y'all to look at this on the next page, okay? We have two really important logarithms. These logarithms have shown up throughout time and we use regularly. The common logarithm, that is log base what? 10. The common logarithm is so common that it is the one log that doesn't have to have a base written with it. If you don't have a base written, it is understood to be base 10. So if I ask for the common log of 1,000, that's still base 10, and what exponent goes on 10 to get 1,000? 3. So the common log of 1,000 is 3. So be aware that this is called the common logarithm. There is also the natural logarithm, which is built on the natural base. What's the natural base? E. So log base b of x is written as ln for natural logarithm. It's actually from a French word, which is why it's L and then N, but it's the natural logarithm of x. So if you see ln, which you should see that on your calculator, right above e to the x in gray, what does it have? ln. It's the ln. So if you see ln, be aware that that is the natural logarithm of x. Alright, listen, I have to assign a little bit of homework that I need you to do. This is on page... thank you. Page 134. I would take a picture of this as you leave today, and I need you to fill out the basic exponential and basic logarithmic function. For those of y'all who are like, I need practice, this is a good set of practice where you would write out the equation and the graph. I will say you would want y equals b to the x, and you would want y equals log base b of x. But sketch out the graph and identify the domain, the range, and we'll discuss this tomorrow. Especially if you think you might have to take the final, make sure you grab a final study guide.
You know, baby, they correctly wake you up too early.
The final study guide, I passed it out at the beginning. So, I need you to complete this on page 134. Make sure you take a picture of it.
Jackson, I was wild.
Have a great rest of your day.
Oh my God,
Anybody need me to leave this up? Yes. What are y'all doing? What y'all trying to break over there?
Don't say y'all. Oh, what happened,
Y'all need me to leave this up today, or do you have a picture of it already? What's up, Jay? So Ian got it for you. Hey, Jaden, we're still planning on having math team after school today, yeah?
Yeah.
You're going in a second. Good morning, Payson. Yes, sir. Good morning, Kennedy.
Okay.
Glad to hear it. Good morning, Inslee.
I'm capable.
Yes, ma'am.
Skinny, is this camera on?
You know, it's a great question. I think it is. I don't think I've stopped it yet.
Why don't you record our class?
Well, because I put the videos together during